everybody, welcome back to LeetCode Simplified. I'm Alan and today we're tackling LeetCode 225 implement stack using queues. Yes, that's classic puzzle when we turn a queue into a stack. And guess what? We're going to solve it two ways, using just one queue and using two queues. Let's dive right in. I'm going to kick things up with the first approach using only one queue. It's simple, clever, and really elegant. First, initialize our stack with a Python's built-in queue to store all the elements of our stack. If we push 1, 2, 3 in and start popping out, the elements come out in order 1, 2, 3 because the queues are FIFO, first in, first out. Perfect for a queue, but a stack is LIFO, last in, first out. We need a clever way to reverse the order during the push operation to match stack behavior. Here's the clever trick. After appending new element X to the back of the queue, rotate all older elements behind X. Let's append 1 to the queue. Then pop left all elements before 1, then append them to the back of the queue. Let's push 2 to the stack. First append 2 to the back of the queue. Then pop left all elements before 2 and append it to the back of the queue again. Now let's try to push 3 onto the stack. First append 3 to the back of the queue. Then pop all elements before 3 and append back to the queue. After this rotation, 3 is now at the front of the queue, acting at the top of the stack. If we want to pop our stack, it's super simple. Since the newest element is always at the front, we just pop front element. Want to know what is on top of the stack without removing it? Again, just return the front element. And if you want to check if the stack is empty, it's just a matter of checking if the queue itself is empty. See what's happening here? We've taken a queue with its standard operations, append, pop left, and transform it to behave just like a stack. If we push 1, 2, 3 onto the stack, they come out in the order 3, 2, 1, exactly like a real stack. Okay, let's submit this version. Boom, accepted. Wonderful. That's how we implement stack using just one queue. Let's step it up and see how we can implement the same stack using two queues. This approach is equally clever and it gives us another way to control the order of elements while maintaining that LIFO behavior of a stack. First, add a second queue, Q2. Q2 will act as a temporary storage while we reorder elements during push operation. Here's the same rotation trick but using two queues. First, push new element 1 into Q2. Then move all elements in the main queue behind X. In this case, we don't have anything here in the main queue to append to the back of 1. Then swap pointers Q and Q2. The main queue now has the correct stack order and Q2 is empty. Now let's push 2 onto our stack. First append new element 2 to Q2. Then pop left all elements out of queue and append it to Q2. Then swap Q and Q2 pointer. Let's try to put new element 3 onto our stack. First append 3 to Q2. Then pop all elements in Q and append it to Q2. And swap Q and Q2 pointers. The front of the main queue always represents the top of the stack, just like the one queue approach. The pop, top, and empty operations of our stack work exactly the same. If you want to pop the stack, just pop left the queue. And we're done. Alright, let's submit this version. Here's coming moment of truth. Boom, accepted. Perfect. The time complexity is constant big O of 1 for pop, top, and empty operations, and big O of n for push operation. The space complexity is big O of n for storing n elements in queues. That's it for today. If you found this explanation helpful, don't forget to subscribe and check out my other LeetCode playlist for problem explained simply and clearly. Hello everybody, welcome back to LeetCode Simplified. I'm Alan, and today we're going full ninja mode on LeetCode 232, implement queue using stacks. You heard it right, we're going to make two stacks behave like a queue. Let's dive right in. First things first, we need two empty stacks, stack in and stack out for our queue. Think of stack in as our incoming pipeline and stack out as our pop ready line. Our two stacks are ready, let's turn them into a queue. Our queue first operation, push new elements. Easy peasy, just append them to stack in. After pushing in some element into stack in, how do we pop them out in the first in, first out order? Just pop stack out. But if stack out is empty, here comes the juicy trick. Pop everything from stack in and append it to stack out. Pop 3 from stack in and append to stack out. Pop 2 from stack in and append to stack out. Pop 1 from stack in and append to stack out. After popping everything from stack in and append it to stack out, then pop stack out. One first in, one first out. That's exactly our queue behavior. Picking is almost the same, but we're just looking at the front without popping it out. Picking at our queue, we know number 2 is at the front of our queue. If stack out is empty, we do the trick exactly the same as we do with the popping operation. Pop everything from stack in and append it to stack out. Exactly the same trick. Moving on to the last operation of our queue. Check if it's empty. That just means checking if both stack in and stack out are empty. And just like that, element 1, 2, 3 comes out as 1, 2, 3, perfectly following the first in first out order of a queue, even though we are using two stacks. Quick and clean. Alright, let's mark the submit button. Here comes exciting moment. Boom! Accepted. The time complexity is amortized big O of 1, meaning more time moving elements from stack in to stack out, but that's rare. So our algorithms on average cause its operation just big O of 1. Space complexity is big O of n linear because we store all elements in the two stacks. And that's a wrap for today. If you love this explanation and want more LeetCode problems broken down simply and clearly, hit that subscribe button and check out my playlist. I'm Alan and this was LeetCode Simplified. Thanks for watching and catch you in the next one. Good day everyone. Welcome back to LeetCode Simplified. I'm Alan, and in this episode, we're walking through the solution to LeetCode 234 Palindrome linked list. Given the head of a singly linked list, return true if it's a palindrome, meaning it reads the same forward and backward. For example, linked list 1, 2, 2, 1 is palindromes because it reads the same both ways. However, linked list 1, 2 is not a palindrome, since reading it forward gives 1, 2. Reading it backwards gives 2, 1. They are different. The first easy, straightforward approach that comes to mind is to copy all the values into an array, then check if that array is a palindrome. That works, but the array consumes big O of n time, extra space. We can do better. Let's design an algorithm that runs in big O of n time and use only big O of 1 space. Our solution comprises of 3 phases. Phase 1. Find the start of the second half. Phase 2. Reverse the second half. Phase 3. Compare both halves node by node. Let's look at it in details in Python. First, we start by creating 2 pointers, slow and fast, pointing to the same node as head, while fast and fast next are not none. Do. Advance slow 1 step. Advance fast 2 step. Advance slow 1 step. Advance fast 2 step. Advance slow 1 step. Advance fast 2 step. If the linked list has even nodes, our loop will stop when fast ends at none. Slow will be at the start of the second half of the linked list. We then proceed with phase 2, reverse the second half using the classic 3-pointer technique, brief, slow, and NXT. First, set brief points to none. Then, while slow pointer is not none, do set an NXT pointer points to slow next. Revert slow next pointer. Advance brief. Advance slow. While slow is not none, repeat advance NXT. Revert slow next. Advance brief. Advance slow. When slow is none, loop ends. Brief will point to the head of the revert second half of the linked list. We then proceed to phase 3. Compare the first and second halves, node by node. Set left to be the head of the first half, right to be the head of the reverse second half. Then, while right pointer is not none, do if left value differ from right value, return false instantly. Otherwise, advance left and advance right. If every pair of nodes match, the linked list is a perfect palindrome. Return true. In our case, the first half linked list 1, 2, the same as our reverse second half linked list, also 1, 2. So our original linked list is a palindrome. Now, look at the special case when our linked list has odd nodes. Our loop will end when fast stop at the very last node, not none. Slow will be at the very middle node. In that case, we need to skip the middle node by advancing slow to the next node, which is the head of the second half. Okay, we just handled the special case for the odd length linked list. And now everything is all set. Let's hit the submit button and see the result. Moment of truth. Boom! Accepted. The time complexity is big O of n since we traversed the linked list a couple of times. And space complexity is big O of 1 constant, no extra space, just pointer juggling. And that's it for today. We just checked if a linked list is a palindrome in place. Another elegant trick for your linked list toolkit. If you enjoyed this walkthrough and want to keep sharpening your LeetCode problem solving skill, check out my other playlist right here on the channel. I'm Alan and this was LeetCode Simplified. Thanks for watching. Good day everyone, welcome to another solution walkthrough on LeetCode Simplified. I'm Alan and today's topic is LeetCode 226, invert binary tree. Given the root of a binary tree, the task is to invert the tree and return its root. Inverting the tree means we swap every node's left and right subtrees. And that's all there is to it, super simple. For example, swap left and right subtree 2 and 7 of root node 4. Swap 1 and 3. Swap 6 and 9. Let's translate that idea into Python step by step. As always, we begin with the base case. If root is none, there's nothing to invert. Simply return none. Otherwise, swap its left and right child using this concise one-liner in Python. After handling the current node, recursively do the same for the left subtree and then the right subtree. Finally, we return root, which now represents the inverted tree. And just like that, the whole tree is inverted. Let's mark that submit button. Moment of truth. Boom! Accepted. And there you have it. Super easy. We inverted a binary tree using a clean and simple recursive idea. Time complexity is big O of n since we visit every node exactly once. Space complexity is big O of h, where h is the height of the tree due to the recursion stack. This problem beautifully demonstrates how recursive maps directly to the structure of a tree. Its subtree is just a smaller version of the whole problem. If you enjoyed this walkthrough and want to keep sharpening your LeetCode problem solving skill, check out my other playlist right here on the channel. I'm Alan, and this was LeetCode Simplified. Thanks for joining me, and I'll see you in the next one. Good day, everyone. Welcome to another solution walkthrough on LeetCode Simplified. I'm Alan, and today's topic is LeetCode 228 Summary Range. Given a sorted array of unique integers, we need to replace all consecutive numbers with a string, start number to end numbers. And if a number stands alone, we simply record it as a single string. For example, given sorted array of unique integers 0, 1, 2, 4, 5, 7. Numbers 0, 1, 2 are consecutive, so we write this range as a string 0.22. Numbers 4, 5 are consecutive, so we write this range as a string 4.25. Number 7 is a standalone number. We simply write it as a single string 7. The key idea is to detect when a range of consecutive numbers ends, so we can record the current range before starting a new one. We start with 0 as the beginning of our first range. Go through each number in the array. 1 and 2 are consecutive, so we continue. 4 breaks the sequence. We then write the range as a string 0 to 2. Update 4 as the new start for a new range. Continue reading through the numbers to find the new break number. 5 is consecutive to 4, so we continue. 7 breaks the sequence, so we write the string 4.25, the previous number before the current number 7. Update 7 is the new start for a new range. Here's the tricky case we need to take care of. We loop through all the numbers, but the last range has not been recorded yet. We need to record the last range, whether it is a standalone number like 7 or a range of numbers like 7, 8, 9. Alright, let's translate that idea into Python step by step. Begin by handling the else case. If given array is empty, just return an empty array. Next, initialize an empty array to store our result. Let's store the very first number as the start of our first range. Now, we begin loop through each number starting from the second one. A break happens if the current number isn't consecutive to the previous one, meaning it's not equal to the previous number plus 1. Append the range as a string from start to the previous number to the result array if it's not a standalone number. Else, simply append the standalone number as a single string to the result. Then start a new range with the current number. Remember, we record a range to the result when we detect a break, but there's no break in the last range to trigger our recording. We need to record the last range as well. So after the loop ends, append the last range as a string from the start of the last range to the last number if the last range is not a standalone number. Else, if the last range is just a standalone number, simply append that number as a single string to the result array. Finally, return the result. Oh, I spot a small indentation. Okay, corrected. And that's the whole solution with one pass through the array. Let's mark that submit button. Moment of truth. Boom! Accepted. The time complexity is big O of n since we traverse the array once. Space complexity is also big O of n because in the worst case scenario, no numbers are consecutive, so each of the n numbers become its own string. Therefore, the result array stores n elements given big O of n space. A simple, elegant solution that shows how just a few lines of logic can capture the entire problem. If you enjoy this walkthrough and want to keep sharpening your LeetCode problem-solving skills, check out my other videos right here on the channel. I'm Alan, and this was LeetCode Simplified. Thanks for joining me, and I'll see you in the next one. Good day, everyone. Welcome to another solution walkthrough on LeetCode Simplified. I'm Alan, and today we will examine 3 methods to solve LeetCode 231, power of 2. Given an integer n, return true if it is power of 2, return false otherwise. With the exception of number 1, powers of 2 are positive even numbers obtained by repeatedly multiplying 2 by itself. For example, 1, 2, 4, 8, 16, 32, and so on. We are going to explore 3 different ways to solve this problem, starting with the most intuitive and gradually improving our approach toward the most efficient version. Let's start simple with the iterative approach. If n is negative or 0, it's not a power of 2. If n is 1, that's a power of 2. Otherwise, as long as n is divisible by 2, keep dividing it by 2. At the end, if the result becomes 1, return true. It is the power of 2. Because we keep dividing by 2, the time complexity is big O log of n, and the space complexity is constant big O of 1. Alright, let's go ahead and submit this version. Boom! Accepted. Great. This version is the most straightforward, purely mathematical. Now let's express the same idea using recursion so we can practice the recursion concept. Our recursion follows the same logic. First, we again check if n is negative or 0, return false. First recursion base case, if n equals 1, return true. Second recursive base case, if n is not divisible by 2, return false. Otherwise, we keep calling the function with n divided by 2 until we either reach one of the base cases. Alright, let's submit this recursive version. Figure crossed. Voila, accepted. Wonderful. This recursive version is clean and logical. Time complexity is big O of log n, same as the iterative version. However, recursion adds overhead because the function calls stack, so the space complexity is big O of log n. Still, it's a good way to think recursively about the problem. Now, there's one more approach that's both elegant and extremely efficient, but we need to know a few binary tricks. In binary, a power of 2 always have exactly one bit set to 1. Look at the binary representations of 1, 2, 4, 8, 16, and 32. They all have exactly one bit set to 1. If we subtract 1 from a power of 2, that single 1 bit and all bits after it becomes flipped. Then n bitwise n minus 1 equals 0. Let's rewrite the solution using this bitwise logic. Return true n is a power of 2 if it is positive n and bitwise n minus 1 equals 0. That's it. Let's submit. Moment true. Boom. Accepted. No loops. No recursion, just clever binary manipulation. This one-liner runs in constant time and constant space. We just examined 3 different ways to check if a number is a power of 2. Among all 3, the bitwise versions is the most efficient and elegant, but understanding all 3 versions help you see how the logic evolves, from basic division to recursion concept to clean binary reasoning. If you enjoy this walkthrough and want to keep sharpening your problem-solving skill, check out my other videos right here on the channel. I'm Alan and this was LeetCode Simplified. Thanks for joining me and I'll see you in the next one. Good day everyone. Welcome to another solution walkthrough on LeetCode Simplified. I'm Alan and today we're taking a look at 3 solutions to LeetCode 326, power of 3. Given an integer n, return true if it is a power of 3. Return false otherwise. With the exception of number 1, powers of 3 are positive numbers such that repeatedly dividing by 3 will eventually result in 1. For example, sum of powers of 3 are 1, 3, 9, 27, and so on. Look, by definition, 3 is formed by multiply 3 one times. So dividing 3 by 3 one time will result in 1. 9 is formed by multiply 3 two times. So dividing 9 by 3 two times will result in 1. Similarly, 27 is formed by multiply 3 three times. So dividing 27 by 3 times will also end up with 1. We're going to explore 3 different Python solutions: iterative, recursive, and a clever mathematical trick, starting with the most straightforward and gradually moving to the most efficient. Let's start simple with the iterative solution. If n is negative or 0, it's not a power of 3. If n is 1, that's a power of 3. Otherwise, as long as n is divisible by 3, keep dividing it by 3. At the end, if the result becomes 1, return true. It is a power of 3. Because we divide by 3 repeatedly, this algorithm runs in big O of log n time. The space complexity is constant big O of 1. There's no extra storage used. Alright, let's go ahead and submit this version. Boom! Accepted. Fantastic. This version is simple, easy to understand, directly follows the mathematical definition of powers of 3. Now, let's rewrite the same idea using recursion. First, we again check if n is negative or 0, return false. The first base case, if n equals 1, return true. The second recursive base case, if n is not divisible by 3, return false. Otherwise, recursively call the function with n divided by 3 until we hit one of the 2 base cases. Done. Same logic as the iterative version, but elegantly using recursions. Let's submit this recursive version. Finger crossed. Boom! Accepted. Terrific. The time complexity is big O of log n, same as the iterative version. However, recursion adds overhead because of the function call stack, so the space complexity is big O of log n. Still, it's good to be able to think of this problem recursively. Finally, let's see a really fast and clever approach using math. The problem constraint say n must be less than or equal 2 to the power of 31 minus 1. So we ask ourselves, what is the largest possible power of 3 that satisfies this constraint? 3 to the power of 19, because it is the largest possible power of 3 that is less than constraint 2 to the power of 31 minus 1. This means every power of 3, from 3 to the power of 0 up to 3 to the power of 19, divides 3 to the power of 19 evenly. Here is a one-liner solution based on the math we just discussed. If n is positive and divide 3 to the power of 19 evenly, n must be a power of 3. That's it. No loops, no recursion, just clever math. Alright, it's time to smash the submit button. Moment of truth. Boom, accepted. Perfect. This one-liner runs in constant time and constant space complexity. So there you have it. 3 ways to solve LeetCode 326 power of 3. If you enjoyed this walkthrough and want to keep sharpening your problem-solving skill, check out my other video right here on the channel. I'm Alan and this was LeetCode Simplified. Thanks for joining me and I'll see you in the next one. Good day everyone, welcome to another solution walkthrough on LeetCode Simplified. I'm Alan and in today's session, we'll be exploring 3 solutions to LeetCode 342, power of 4. Given an integer n, return true if it is a power of 4, such as 1, 4, 16, 64, and so forth. Except for 1, powers of 4 are positive numbers obtained by multiplying 4 multiple times. Take 4 as an example. It's 4 multiplied once. So by reverse engineering, dividing 4 by 4 one time gives 1. 16 is 4 multiplied twice, so dividing 16 by 4 2 times also equals 1. 64 is 4 multiplied 3 times, so dividing 64 by 4 3 times results in 1 as well. We are going to explore 3 different Python solutions: iterative, recursive, and a clever mathematical approach, beginning with the simplest and working up to the most optimal solution. Let's kick up with the iterative method to get a solution foundation. First, if n is negative or 0, it cannot be a power of 4. If n is 1, return true. 1 is a power of all integers. Otherwise, as long as n is divisible by 4, keep dividing it by 4. At the end, if n becomes 1, return true. N is a power of 4. Since we divide by 4 repeatedly, this algorithm runs in big O of log n time. The space complexity is constant big O of 1 as no extra storage is used. Let's go ahead and submit this version. And there it is. Boom! Accepted. Awesome. This version is straightforward, easy to understand, and directly follows the mathematical definition of powers of 4. Now, let's rewrite the same idea using recursion. First, we again check if n is negative or 0. If so, return false. As in recursion, always establish base cases to stop the function from calling itself endlessly. The first base case, if n equals 1, return true. The second base case, if n is not divisible by 4, meaning the remainder is 1, 2, or 3, return false. Otherwise, recursively call the function with n divided by 4 until we hit one of the two base cases. There it is, recursion in action, following the power of 4 definition to the letter. Submitting time. Boom! Accepted. Perfect. The time complexity is still big O of log n, same as the iterative version. The difference is recursion adds big O of log n space overhead for the function called stack. Still, thinking recursively is a great exercise for coding skills. Finally, we use a clever mathematical trick powered by bitwise operations. It's lightning fast and skip both loops and recursion. Before we dive into the code, there are two key deductions to keep in mind. First, all powers of 4 are also powers of 2. That's because 4 to the power of x equal 2 to the power of 2x, and 2 to the power of 2x is clearly a power of 2. So, how do we pick out powers of 4 from all the powers of 2? We need a second deduction. A power of 4 minus 1 is always divisible by 3 because 2 to the power of x minus 1 and 2 to the power of x plus 1 differ by 2, so one of them must be divisible by 3. Therefore, their product is divisible by 3 as well. For example, let's examine the power of 4, number 16. 16 minus 1 equals 3 times 5. 3 is divisible by 3, then 15 is also divisible by 3. How about 64? 64 minus 1 equals 63, or 7 times 9. 9 is divisible by 3, so is 63. What about this power of 4? 1048576. From our first deduction, it's also a power of 2, or equal 1024 squared. So after subtracting 1, why is the result divisible by 3? Let's do some math here. 1023 and 1025 differs by 2. So either 1023 or 1025 must be divisible by 3. Then their product is also divisible by 3. Therefore, the power of 4, 1,048,576 subtract 1 is also divisible by 3. Combine these two deductions helps us further distinguish powers of 4 from the rest of powers of 2. If n is positive and if n is a power of 2, meaning n bitwise n minus 1 equals 0. And then second check if n minus 1 is divisible by 3. If so, then n is a power of 4. Done. All wrapped up. It's time to smash the submit button. Moment of truth. Boom. Accepted. Perfect. And just like that, no loops, no recursion, just smart bitwise logic in constant time and constant space. So there you have it. 3 ways to solve LeetCode 342, power of 4. Enjoy this video? If this walkthrough got your gears turning, keep the engine running. Click over to my other videos and we keep smashing coding challenge together while sharpening our problem-solving skill. Thanks for joining me, and I'll see you in the next one. Good day everyone, welcome to another solution walkthrough on LeetCode Simplified. I'm Alan, and today we're going to explore 4 different ways to solve LeetCode 242 valid anagram. Given 2 strings S and T consists of only lowercase English letters. Return true if T is an anagram of S, meaning each character has the same frequency in both strings. Let's look at the examples. String S has 3A, 1 N, 1 G, 1 R, and 1 M. String T had the same character counts, so these 2 strings are indeed anagrams. On the other hand, string rat has 1 T, but string car has no T. Clearly, these are not anagrams. Now that we have a clear understanding what an anagram is, let's dive into the solutions, starting with the simplest one. The most straightforward approach is to sort the strings. First, a quick check. If S and T have different lengths, there's no way they have the same character counts. Therefore, they cannot be anagrams. Otherwise, if their lengths match, we simply compare the sorted versions of the 2 strings. If the 2 sorted strings are identical, they are anagrams. Simple enough. Let's go ahead and submit the first version. Boom. Done. This version runs in big O of n times log n because of sorting. The space complexity is big O of n to store the sorted strings of n elements. Sorted works fine, but can we do better? Absolutely. For a linear time solution, instead of using Python sorted function, we can leverage Python counter from the collections module. First, check lengths of S and T as before. Leverage Python counter to count the frequency of each character in both strings and compare. That's it, as simple as the first version. Time for submitting, and voila! The time complexity is linear big O of n, faster than sorting, especially for longer string, since we avoid the sorting step. And the time complexity is big O of k, where k is the number of distinct characters. How about an even better solution using constant space? You bet. Here's the idea. Use an array of fixed size 26 to store the counts of each character. First, initialize the array. Loop through each character in S and increment its count. Loop through each character in T. Find its index based on the ASCII distance from character A. Then subtract 1 occurrence from its count. Now check if T has more of this character than S. We exit. S and T are not anagrams. This crucial step skips a big loop if string T is large. At this point, we have looped through string T and all character counts match string S. Return true. They are anagrams. Let's submit this version. And boom, accepted. Perfect. This version runs in linear big O of n time. Space complexity is constant big O of 1 for the fixed size array count. This is efficient both in time and space, but it only works for lowercase letters. What if the strings contain Unicode characters, anything at all like numbers, emojis, symbols, etc.? In that case, we switch to using a dictionary because it can handle any character type. Here's our approach. First, create an empty dictionary to store the counts. Now, loop through each character in S and increment its count. Then loop through each character in T. If it's not in the dictionary, return false at once. Else, decrement its count and check if its count drops to 0. Delete the character from the dictionary. Finally, after processing T, if the dictionary is empty, meaning each character has the same frequency in both strings, the 2 strings are anagram. Alright, let's submit our 4th and final version. And voila, accepted. Great work. This version works for any character set and adapts dynamically, making it very versatile. So there you have it, 4 ways to solve LeetCode 242 valid anagram. Enjoy this video? If this walkthrough got your brain in spin, keep on coding, let the fun begin. Click over to my other videos and we keep smashing coding challenges together while sharpening our problem solving skill. Thanks for joining me. I can't wait to see you in the next one.
Tell me when you will be mine. I'm teasing. Relax. Okay, Alan, what are we solving today?
Good day, everyone. Welcome to another solution walkthrough on LeetCode Simplified. I'm Alan, and today we're going to explore two different ways to solve LeetCode 257 binary tree path. Given the root of a binary tree, return all root to leaf paths in any order. For example, this tree has two leaves, so naturally we get two paths. The first path goes from root 1 down to leaf 5, and the second path goes from root 1 down to leaf 3. Therefore, the resulting paths are. When dealing with the tree problems, recursion often feels like the most natural fit. So let's jump right in with the most common and cleanest approach, depth first search using recursion, where we build the path string as we traverse down the tree. We'll start by creating an empty array to store all our root to leaf paths. Next, create our helper function to handle both the recursive traversal and the path building logic. We will call it with the root and an empty initial path. Now let's walk through what our helper function does exactly. If node is none, that means we hit an empty pointer. Simply exit. If no left child and no right child, meaning it's a leaf, we finalize the path by appending to the paths array the current path string concatenated with current node value, and then exit. Otherwise, this node is not a leaf, so we continue building the path string by adding the current node value, followed by an arrow. Then we explore left subtree and right subtree. After all the recursive calls finish, return the list containing every root to leaf path strings. Okay, let's give it a try. Hit submit, and boom, accepted. This recursive depth first serve approach is one of the cleanest patterns you see for top-down tree problems. Time complexity is big O of n because we visit each node once. Space complexity is big O of h, where h is the height of the tree due to recursion stack.
That's great, Alan. But can you do it without recursion?
Absolutely, Lucy. Let me demonstrate a breadth first search perspective, an interactive method that avoids recursion entirely. We leverage the deck module from Python collections packet to store tuples of nodes and the path string leading to them. Let's begin. If root is none, that means there's no tree and no paths. Simply return empty array. Initialize an empty array to store our path strings. Initialize a queue using a tuple containing the root and its values at the starting path. As long as the queue isn't empty, pop from the left and unpack the tuple into two variables, node and path. If this node is a leaf, add the path to the answer. Otherwise, if it has left child, append a tuple of the left child along with the extended path. Likewise, if it has right child, append a tuple of the right child along with the extended path. When the queue is empty, all root to leaf paths have been collected. Return our path list. That's it. Let's hit the submit button. And boom, accepted again. The time complexity is big O of n because we visit each node once, and the space complexity is big O of n also, in the worst case because the queue can hold multiple nodes across levels. So there you have it, two solid ways to solve LeetCode 257 binary tree paths, a clean recursive depth first serve solution, and iterative breadth first serve solution using a queue. Enjoy this walkthrough? If this video got your problem solving gears spinning, keep the momentum going. Check out my other videos and together we keep smashing these coding challenges.